Welcome to Mrs. Lee Chemistry Academy. Today we're going to focus on concentration and rate laws. Tying to the learning objective from College Board 4.2, the student is able to analyze the concentration versus time data to determine the rate order for a zeroth, first, or second order reaction. 4.3, the student is able to connect the half-life of a reaction to the rate constant of a first-order reaction and justify the use of this relation in terms of the reaction being a first-order reaction. Now, first, we will deal with the differential rate law. The rate law expresses reactant rate as proportional to the concentration of each reactant raised to a power where K is the rate constant. So rate is equal to K times reactant 1 raised to the power M times reactant 2 concentration raised to the power N, where the power M and N is the order in individual reactant and the overall order of the reaction is M plus N. The unit of K in lowercase is very important. It depends on the rate order, because the rate constant is equal to rate divided by the concentration of the reactant raised to some power. So for zero order, the rate is equal to K because there's no concentration to be concerned about, and therefore K has the unit of molarity per second or molarity per time. For first order reaction, rate is equal to K times concentration of A raised to the first power. Therefore, K is equal to rate divided by A, meaning second minus 1. Second order reaction, rate is equal to K times A raised to the power 2. So K is equal to rate divided by A raised to the power 2, which ends up to be molarity minus 1, second minus 1. Now when you do this, please don't try to memorize it, but try to deduce it in terms of the order of the reaction. Order reaction can only be determined experimentally by the method of initial rates, rate for a short period of time at the beginning, and it cannot be related to the stoichiometric mole ratio in a balanced reaction. Consider the reaction 2 moles of NO reacting with 2 moles of hydrogen to form 1 mole of N2 and 2 moles of water vapor. Determine the rate law and the rate constant with units. Now here are the data given. So first we use the logical argument. If we look for trial 2 and trial 1, in which the concentration of NO is held constant, but the concentration of hydrogen is doubled, and the rate is doubled. Therefore, we conclude the rate is first order with regard to hydrogen concentration. Now you pick the other two trials, trial 3 and trial 1, in which the hydrogen concentration is held constant, the NO concentration is doubled, and the rate is increased by 4 times, which is to the power 2. Therefore, we say the reaction is second order in NO. And then when you write the overall rate law, is rate is equal to rate constant times NO raised to the power 2 times hydrogen raised to the power 1 concentration. And when you calculate the rate constant, we will then divide the rate by the respective concentration and raised to the certain powers, and we just can pick any trial number, any data from any trial, and in which case I have picked trial 1. And don't forget that NO has to be raised to the power 2, while hydrogen is raised to the power 1. In concentration, we have obtained 2.53 times 10 to the minus 3, molarity minus 2, second minus 1. Now there's an alternate solution by mathematical analysis. Here we are. Now we do the ratio of the rate 2 to rate 1 equal to the rate law expression on the right hand side, and we substitute the numbers in. And be sure when you write the rate law, it is the concentration of NO raised to the power M and H2 raised to the power N. Now in this case, we can cancel out the K, the rate constant, and the 0.1 molar from NO. And then we have, then on the left-hand side, we have the rate ratio, which is 1.99, equal to the right-hand side, the molarity ratio, which is 2 to the power N. Therefore, N is 1, rate is first order in hydrogen. Then we compare rate 3 with rate 1 in a similar fashion. And then when we cancel out this 0.1 molar that stays constant in the hydrogen concentration, we find that to the left, the rate ratio is 3.99, which is almost 4. And to the right, we have the rate ratio, or the molarity ratio, which is 2 to the power m. Therefore, we conclude m is second order. And we write the rate law. Rate is equal to k, rate constant, times NO raised to the power 2, and H2 raised to the power 1. Now, I asked my student which way do they prefer. Some like the logical argument, some like the mathematical derivation. It's up to you which one you want to choose. Now we're going to talk about the second kind of law, rate law, which is called the integrated rate law, because it ties the concentration to time. The concentration is dependent on time. Now remember, in the first order reaction, when we write the differential rate law, rate is equal to rate constant k times a raised to the power 1. Now let's take that information, okay, and we're going to plot this line here of natural log of a versus time. Now we get a straight line going downhill. That means this is first order with regard to the concentration of A, and this is a proof that it is first order. Now this is a linear relationship, therefore y is equal to mx plus b. Now y is your natural log of A at certain time, m is the slope negative k, and x is the axis time t, and b is the intercept natural log of A at time 0. Substitute it into the linear equation, you will have natural log of A, concentration at time t, equal negative kt plus natural log of A at time 0. Now this is the integrated rate law for first order reaction. And then you can further group it into natural log of A at time t over A at time 0 equal to negative kt. Another thing we need to derive is the half-life, which is the when the concentration of A is half of the original concentration. When you substitute all that into the equation, we find out that half-life is 0.693 over k. Now this is a constant, meaning half-life does not change. It's the same throughout different parts of the experiment. Practice problem number 1. What is the order for the decomposition of hydrogen peroxide? And determine rate constant with unit, calculate concentration after 1200 minutes, calculate half-life. Here is the data chart. I have already converted the concentration of hydrogen peroxide into natural log values. And I have made a graph here. The plotting of natural log of hydrogen peroxide concentration versus time result into a straight line with a downhill slope. Therefore, we can conclude that this is a proof that the reaction is first order. Now, when we plug the numbers into the integrated rate law for the different concentration at time 0 at 800 minutes, we can then calculate the rate constant to be 1.06 times 10 to the minus 3 per minute. And then now we want to calculate the concentration of hydrogen peroxide. After 1200 minutes, we plug the numbers in with the rate constant, 1200 minutes, and the concentration natural log of that at time 0. We calculate it to be 5.61 times 10 to the minus 3 molar. And finally, the half-life is 0.693 over k, the rate constant, 654 minutes. Second order. When the rate is second order in the concentration of A, we write rate equals k times A raised to the power 2. Now, if we plot 1 over A concentration versus time, we get a straight line going uphill with a positive slope. This is a proof that it is a second order reaction, and therefore using the linear relationship we can derive the rate law being 1 over A concentration at time t equals kt, the positive slope, plus 1 over A concentration at time 0. And then we can further derive the half-life. You can follow my derivation. Half-life is equal to 1 over the rate constant k and that of concentration of A at time 0. Now please note that the half-life depends on initial concentration and becomes larger or longer as concentration decreases. So this is the difference between first and second order half-life. First order half-life is constant. Second order half-life actually becomes longer. Practice problem number 2. NO2 decomposes at 300 degrees into NO and half a mole of O2. Now, given this data, which I have taken the liberty of converting into 1 over the concentration of NO2 and generated some numbers, and use the data to confirm it is a second order, and write the rate law expression, calculate rate constant with units, find concentration of NO2 after 645 seconds, and determine half-life. So here's the plot of 1 over concentration of NO2 versus time, resulting into a straight line with a positive slope going upward, a proof that it is second order. Going further on the calculations, so from the differential rate law and the integrated rate law, now we can plug in the values. 1 over NO2 at time 0 is 100, and 1 over NO2 at 300 seconds is 263 molarity minus 1. And plugging in the time of 300 seconds, we now calculate the rate constant to be 0.543 molarity minus 1, second minus 1. And then determining the concentration of NO2 after 645 seconds, plugging into the formula of the rate constant K, and we come up with 2.22 times 10 to the minus 3 molar. And the half-life is equal to 184 seconds. Zero order reaction. That means rate is independent of the reactant concentration. So rate is equal to K, because whatever raised to the power 0 is dropped out as a 1. So in this sense, the plot of A versus time will yield a straight line. And when we obtain a plot as such, we conclude it's zero order, and the rate law is A concentration equals minus KT plus A at time 0, and the half-life is A concentration at time 0 over 2K. So half-life actually shortens as concentration decreases. So here's a summary table, which is really important for students to understand. Here I have lined up zero order, first order, and second order. With regard to rate law, integrated rate law, the plot to get a straight line, the relationship of the K to the slope, and the half-life. And I have put 3 asterisks to 3 equations, such as first order integrated rate law, second order integrated rate law, and the half-life for first order. Now these 3 equations will be given on the formula sheet when you take the AP Chem exam. When you plot the rate as a function of concentration of A, when it is zero order, it will be a horizontal line. That means no matter what the concentration is, it doesn't affect the rate. Then if it's first order, it will be then going up at a 45-degree angle, like a diagonal, a linear relationship. As concentration A is doubled, rate is doubled. And then when for second order, that means it's going up exponentially. As A concentration is doubled, rate is increased by 4 times. Therefore, you see that blue line going up exponentially. Practice problem number 3. For the decomposition of hydrogen peroxide, it is first order. The right graph shows concentration of hydrogen peroxide as a function of time. What's the average rate between 0 and 50 seconds? And how many moles of O2 are formed in 50 seconds if the volume is 3 liters? And calculate rate constant with units. Estimate half-life from the graph. And show me the graph if it is repeated at a lower temperature. So now let's take a look at the graph. We're starting at 1 molar concentration, and when it's decreased to half a molar, and you look at the time, it's approximately 23 seconds. So we need to mark those numbers. And then when it's going down to 0.2 molar, the time is about 50 seconds. Mark those numbers when we go further in the calculation. Now remember, I said earlier that we marked that over 50 seconds, the molarity has declined from 1 to 0.2 molar. So the rate of disappearance of hydrogen peroxide is changed from 1 to 0.2 molar over 50 seconds, or 0.016 molarity per second. And also going back to the stoichiometric mole ratio, as 2 moles of hydrogen peroxide disappear, 1 mole of oxygen forms. Therefore, we can use the rate of disappearance of hydrogen peroxide times the mole ratio of 1 over 2 times 3 liter being the volume times 50 seconds, and we get 1.2 moles of oxygen formed over that time period. Then we use the integrated rate law to find the K rate constant. Plugging into 0.2 molar and 1 molar and 50 seconds in time, we get the rate constant 0.032 per second. The half-life, as I said earlier, if we go to 0.5 molar, the corresponding time is about 23 seconds. And then when we want to plot the graph, here I have the dotted line representing the rate over lower temperature, because at a lower temperature, the rate of decomposition will slow down, will decrease, so the concentration of hydrogen peroxide would be higher at a given time, represented by the dotted line. Practice problem number 4. Student uses colorimetry and Beer's law to investigate if the decomposition of a colored species X is a first-order reaction. Design an experiment, perform graphical analysis of the data, write the rate law expression, calculate the value of K with units, and determine the half-life. Now, in terms of designing the experiment, first, I would, because I'm using Beer's law, I would have to make some zero dilution to make several standard solutions in order to generate the line of best fit. So I'm starting with a 0.25 molar stock solution and dilute it down to 0.05, 0.10, 0.15, and 0.20 molar, each having 10 milliliter. And you can work out the math in doing this. Now, when I have all the standard solutions ready, I'm going to take it to the colorimeter and determine the absorbance by putting them into little cuvettes at 565 nanometer, which gives me the maximum absorbance. Then I use the data to plot a line of best fit of absorbance versus concentration. So that's my standard curve. Now I'm ready to work with my sample X. I will react it with an excess reactant that's much more in excess that will cause the color of X to fade over time. And I'm going to monitor the decrease in absorbance in the colorimeter. And then I'll make use of that data to plot absorbance versus time for X. Now finally, I would have 2 graphs, one being the standard calibration curve and the other being absorbance versus time, and I can extrapolate data from both graphs to find the natural log of the concentration of X versus time to prove that it is indeed first order. So here, I need to explain that quite carefully, and please follow my explanation. On the left-hand side, I have the standard calibration curve that I'm measuring the standard solution, 0.05, 0.1, 0.15, 0.2 molar at different absorbances, ranging from 0.24, 0.42, 0.68, and 0.85. So now you have a standard calibration curve represented by the left graph of a straight line going up. All right, in the middle graph, now I have this X, and which reacted with an excess reactant, and I'm tracking the absorbance over time. So starting with half a minute, the absorbance was 0.7, 1 minute, 0.5, 1.5 minute, 0.36, and so on until 3 minutes have gone by down to 0.12 absorbance. And I use that data to plot a curve. Now, the third one to the right is extrapolation of data from the 2 graphs. First, I go to the 0.05 molar, and I take the natural log of that, that's equal to negative 3.0. Now, because the 0.05 molar from the left graph corresponds to absorbance of 0.24, so I now come to the middle graph and I look for absorbance on 0.24 for the corresponding time and find it to be 1.9 minutes. And I do the same thing for every set of data. For example, the last set of data, which is at 0.2 molar, so I take natural log of 0.2, which is negative 1.6 value. Now the absorbance is 0.85 from the left data. So I go to the middle one, go to 0.85 absorbance, and find the corresponding time, and that's 0.25 minutes. Now I have enough points to make my graph on the right of natural log of X concentration versus time, and I get a straight line going downhill, that means the reaction is first order. So in terms of calculation, I write my differential rate law. Rate is k times x raised to the power 1. Then I have my integrated rate law. I'm doing the time between 0.25 and 1.9 minutes. And initial concentration, natural log is negative 1.6. And the final concentration, natural log is negative 3.0. I have the rate constant being 0.85 per minute. Now to do the half-life, it is 0.693 over the rate constant, which yields a 0.82 minute. And this is a constant half-life characteristic of a first-order reaction. So let's sum up what we have learned today. We learned how to derive differential rate law by comparing experimental data in which one reactant concentration is kept constant while the other reactant concentration is varied. We used graphical analysis of concentration versus time to determine the integrated rate law for a zeroth, first, or second order reaction. We further determined the value of rate constant K for each kind of reaction with the respective units. Then we calculate the half-life for various reaction orders. And finally, we end up with a design of the experiment based on fading of reactant color to determine the reaction order using Beer's law and a colorimeter. Now when you're doing the lab in your class, you may recall the lab on the fading of the crystal violet, and that's pretty much along the same kind of concept and idea on my point number 5. So from the team of MLCA, we want to thank you for watching our video, and we certainly hope to see you again next time.